Hey, physicists. So, at first, I just want to say thank you very much for taking the time to watch these videos to really figure out this physics. I know that the weather has kind of thrown us a curveball as we've been going through this unit, and I want to say thank you very much for your dedication to getting the physics figured out. So at the end of the day on Friday, with our super short day, we had just done the ramp problem. The discussion that I had on the last video looked like this. So we had the ring and the small disk and the large disk, and we raced them down, and we were trying to see who was winning, right? And it turned out that the smaller disk wins every time. And we started talking about the idea of rotational kinematics. So I wrote this down wrong. That's super embarrassing. I apologize. I'm glad I popped back here. This is translational kinetic energy, and this one right here is rotational kinetic energy. So they're related, and the important thing to really know, taking away from what happened in class on Friday, is that as an object is going down a ramp, if it's rolling, not only does it have that translational kinetic energy where it's moving in space, right, moving across a distance, but it also has rotational kinetic energy, and that part has to be taken into account as well. Okay, so in order to kind of continue that discussion, I wanted to look a little bit more closely at the ramp situation. So I'm going to go ahead and draw this. I would love for you to have your notes out so that you can draw this with me. So here's my ramp. It's got some certain height. We'll call that height H. And I am going to race three different objects. So object number one is just going to be a box. Okay. And when this box slides down, we're going to assume that it slides with no friction. And I'm going to say no friction. So no loss of energy to friction as it's going down. The second object that I've got is going to be a disk. Okay. And that disk, as we said yesterday, all of the disks and rings that are going down a ramp do have to have friction, right? There has to be friction in order for them to spin. Otherwise, they wouldn't spin. They would just slide down the ramp like the block does. Okay. So there's a disk. Should label the box. And then the third one that we're going to do is a ring. So it looks like this. And for our purposes today, we are going to say that all three of these have the same mass, just for simplicity's sake. Okay. Now, I'm just going to remind you that we spent much of our day on Friday analyzing two different pieces. So this was Paul and Kathleen. We asked which one is traveling faster at the bottom and then which one makes it to the bottom first. So on Friday, at the end of the day when we were doing our demo, we did talk about who made it to the bottom first, but we didn't ask who's moving faster at the bottom. We decided with the warm-up problem, and the reason we did this warm-up problem was very intentional, that in Paul and Kathleen's case, they're not rolling, so there's no rotational kinetic energy. They will have the same speed at the bottom, right? Because they've got the same height at the top. All of that potential energy is converted to kinetic energy. And so regardless of mass, if they have the same height at the top, they're going to have the same speed at the bottom. The question is, when we've got things rolling, is that the case? That's what we're going to figure out today. Spoiler alert, it's not. Haha. All right. So we're going to start with the box because we know the box well, right? In each of these cases, we know that the total energy at the beginning has to equal the total energy at the end. I'm going to write it out every time. I would encourage you to as well, because the more practice you have with this, the better. So the gravitational potential at the beginning plus the kinetic at the beginning has to equal the gravitational potential at the end plus the kinetic at the end. And in this case, just to be clear, we need to actually write little k sub t there for translational. The box is not tumbling down, and so it's only got translational kinetic energy. We've done this problem a million times, so I'm going to go pretty fast through it. There's no kinetic at the top. There's no gravitational at the bottom because we're going to set h equals 0 right there. So we've got the mass times the acceleration due to gravity times the height at the top, or initially, is equal to 1/2 mv final squared at the bottom, and those masses are going to cancel. We can figure out how fast this box is going. We've done this a bunch of times. It's the square root of 2gh. So that is the final velocity for the block at the bottom. Easy, no problem. It can be Paul, it can be Kathleen. In fact, it doesn't matter how big the box is, it's still going to have the same velocity at the bottom. Now, let's take a look at the disk. For the disk, the same thing is true in that the energy total at the beginning has to be equal to the energy total at the bottom, okay? The friction is present, but it's not actually rubbing, it's just causing it to rotate. So there's no change in energy from the top to the bottom. So we know that the gravitational at the top plus any kinetic at the top has to equal the gravitational plus the kinetic at the bottom. Now, instead of just writing equals here, though, I'm going to go ahead and write this as translational and rotational, okay? Because it matters. Just wait, you'll see why. So UG final plus kinetic final for translational plus kinetic final for rotational. I guess I wrote those backwards last time and I apologize. So let's take a look at here what's going on. So we can say that at the beginning there is no kinetic energy of either type, and at the end there is no gravitational of any type as well. So we've got the same sort of situation here. This is mgh at the beginning is equal to, now this is where it gets a little bit interesting, right? We've got both translational and rotational kinetic energy at the bottom. So the translational is just 1/2 mv squared, just like it always is. But now we also have kinetic energy that is tied up in rotation. That's going to be the 1/2 I omega squared. So in order to figure out what to do with that, we need to figure out what I is. And I, in this case, for a disk, let's go ahead and take a look way up here, moment of inertia. I think it's right there, okay? For a disk is 1/2 mr squared, okay? So we're going to go ahead and write that down. I need to find where I'm at here. I think there we are. Okay, so this I, I'm going to, let's see. I'm going to write this all out again one more time. So mg equal to 1/2 mv final squared plus 1/2. Now this is 1/2 mr squared. And then we've also got this omega thing. We're going to remember that omega is equal to v over r. So any place I see an omega, I can write v over r. That's really convenient because then I can write this as v squared over r squared. And you're probably going, oh, I see what you did there, Miss K, right? Because there's an r squared in here and there's an r squared out there. So that's going to be really nice. So we can write the right-hand side of this equation is now 1/2 mv final squared plus 1/2 plus 1/2, that's 1/4 mv final squared. So on the right-hand side of our equation here, we've got 1/2 plus 1/4 is 3/4, right? So we've got 3/4 mv final squared is equal to mgh. M's are going to go away, and we can solve then for the velocity, the final velocity for the disk. Just a reminder here, we're talking about the disk, okay? V final for the disk is going to be equal to the square root of, it's going to be 4/3 GH, okay? So right away, without even doing much work here, we can see that the final velocity for the block, the thing that's just sliding down, is different than the velocity for the disk. In fact, the block is higher, right? Because we've got a 2 in here versus a, oops, that should be, yeah, yep, 4/3, which is, 1 1/3, not quite 2. All right, so we've got 2 different velocities there. And then let's try the other one just to see what's going to happen. So again, things are a little different when you add this this rotational kinetic energy situation into the mix. So let's go ahead and do the ring. So again, start with the same thing. E total initial equals E total final. We've got UG plus KT plus KR equals UG plus KT plus KR. Y'all know that that's initial and final, right? So we're going to go ahead and get rid of this one. See you later. That one, this one, and we're going to cruising on through. So this is mgh initial is equal to 1/2 mv final squared. So that's the translational part of the disk situation. Plus we've got 1/2, oops, yeah, 1/2 I omega squared final. Again, we need to look and see what our moment of inertia is for a disk, or excuse me, for a ring. So a ring is going to be a thin-walled hollow cylinder, which indeed is mr squared. So there's no fraction in front of it. It's just straight up mr squared. And so let's go back to our um, situation over here. So we got mgh is equal to 1/2 mv final squared, plus this is going to be 1/2. This is just mr squared. And then again, just like it happened over here, this is going to be v squared over r squared. R's are going to go away. See you later. And so in this case, we've got, well, that's going to be what? 2/2 or 1. So this is just going to be mgh initial is equal to mv final squared. Easy to solve for that. M's are going to go away. We can see that V final in this case is equal to just the square root of, oh, I'm so used to writing a 2 there. Oops, sorry about that. GH. Okay. And so now from this analysis, this pretty quick analysis, we can see that in each of those cases, the velocity is different. We can see that if we race those three things down, in fact, unlike Paul and Kathleen, who no matter their trip, they have the same velocity at the bottom. That is not the case for our three things. We see that the velocity for the block is greater than the velocity for the disk, which is greater than the velocity for the ring. Okay, pretty cool. All right, there are a few ranking tasks. I put a worksheet up. Go ahead and work on as many of those as you can, and then I'll put up quick videos to help you out with those too. Again, thank you for your dedication. Thank you for your time and your effort, and let me know what questions you have. I'm very happy to go through this stuff more. Have a great day.